In this video, we are going to extend our definitions of acids and bases and learn about what we call nucleophiles and electrophiles. Up until this point, we've been talking about an acid reacting with a base to produce a conjugate acid and a conjugate base, and the acid was always the proton donor, right? And the base was always the proton acceptor. And that's generally how you studied acid-base chemistry in general chemistry as well. And this is not incorrect, it's just not quite complete. In this class, we're really going to be interested in the movement of electrons. And so the way that we want to start defining an acid or a base is not just in terms of something that can give a proton or take a proton, but rather what is it doing with its electrons. And so, for example, I'm going to show you the notation that we're going to use to track electron movement here. And let's take a look at this acid-base reaction that was in the previous slide. So rather than thinking of HA as being a proton donor, we're really going to start over here with the lone pair of electrons on the base. And during the course of the reaction, notice that the bond between H and A is broken, and the bond between H and B is formed, right? And you also end up with a negatively charged conjugate base. So we're going to take a look at how all of these steps happen. So let's take a look at what's actually going on here during the course of this reaction. The lone pair on the base is actually what initiates the entire process as far as we're concerned. And notice that it's going to form a bond to this hydrogen over here. So what happens is the lone pair migrates over and attacks the proton of the acid, and we're using this full-headed arrow notation, as we always will in this course, to indicate two electron movement. So we're showing that the two electrons that were on the base, the lone pair, have now migrated over and are attacking the proton of the acid. Since this proton cannot have two bonds at once, it needs to break the bond between itself and A. And so the sigma electrons that were being shared between the two are now going to migrate over to A, and that's what's forming the conjugate base over here. So the lone pair that is now on A was originally the sigma bond here, and the sigma bond that is now between H and B originally was the lone pair here. Now what we need to do in the next slide is to take a look at what this has to do with acidity and basicity. So we established in the last slide that it's the lone pair on B that's coming over and attacking the proton of the acid. And so we could say that the base is donating its electron pair. So it's acting as an electron pair donor. At the same time, the proton on this side, the H atom, is accepting the electron pair from the base. And so we're going to say that HA is acting as the electron pair acceptor. And it's really going to be this idea of electron pair donor and electron pair acceptor that we're going to pay the closest attention to when we start studying various reactions throughout the course. And as far as we're concerned, any species that accepts a pair of electrons is going to be an acid. So acids accept electrons. And any species that donates a pair of electrons is going to be a base. And so bases are electron pair donors. So this definition of acid and base allows us to look at acid-base reactions that don't involve a proton transfer. So for example, if you were to put BF3 in with water, you would see that the following reaction would take place. You would get a lone pair from oxygen attacking the boron atom to now give you a new boron-oxygen bond. Boron still has all of its fluorine atoms attached to it, and we're going to go ahead and fill in all of the lone pairs just to be thorough here. Oxygen still has both of its hydrogens attached. It only has one lone pair now because it gave the other one to boron. That's what they're sharing here. That's what is forming the new sigma bond. And we're not quite done because these are not going to have neutral charges. Oxygen is now in a +1 state and boron is now in a -1 state. If you can't remember how to assign formal charges to atoms, this would be a good time for you to go back and review those principles. But you have an overall net charge of 0 on the left, so you know that you have to have an overall net charge of 0 on the right. If we take a look at this from the perspective of who's donating and who's accepting electrons, well, the water is clearly the one that is donating electrons. So this is going to be the base in the reaction. It's using its lone pair to attack the boron. The boron is accepting the electron pair from oxygen, and so it is acting as the acid, in this case, BF3. So we're going to continue to look at acid-base reactions from the perspective of a base being an electron donor and an acid being an electron acceptor. So let's take a look at an example of one that you should know from general chemistry. We have hydrochloric acid and water. And hopefully you remember that, well, hydrochloric acid is a very strong acid, so it's obviously going to give up its proton to water. And so you should end up forming H3O plus and Cl minus. I'm going to go ahead and draw in the lone pairs here. And there we have our balanced equation. But let's take a look at this in terms of electron donating or electron accepting. If we know that HCl is acting as the acid, therefore water is acting as the base, our new definition tells us that this base must be the electron pair donor. And the acid must be the electron pair acceptor. The new bond is between the oxygen and the proton over on this side. And so what's happening is the electrons from the oxygen are attacking the proton here. The electrons that are being shared between H and Cl are migrating over to Cl to generate Cl minus. And so you can see that in terms of not only proton transfer, but electron transfer, these fit the definitions of acid and base. Now let's use an example with a couple of organic molecules. If you're looking at this reaction, we have to find something that can donate electrons and something that can accept electrons. Clearly, there aren't really any electrons over here in this structure, this carbocation, that would be donatable, so to speak. It looks like the electron source is going to be the lone pairs on this oxygen. So hopefully you'll start to kind of get a feel for, well, that looks like that has to be the base and this has to be the acid, because I can figure out where the electrons are located, and then we need to think about, well, what are they going to do? So if we know that the base is the electron pair donor, we're assuming that we're going to start drawing an arrow from here, but the question is now, where does it go? And if you're taking a look at this structure and we need to find a place to put a pair of electrons, this carbon atom right here with the positive charge is our best candidate. Not only because it has a positive charge, but because it has an incomplete octet at this point, and so it would be able to pick up that extra pair of electrons. And so if we were to write out the products of this reaction, we would have CH3, C, CH3, CH3, new bond to oxygen, which still is holding on to its groups. It has one lone pair of electrons now, and it now has a positive charge. So this would be the product of the acid-base reaction shown above. So it's not always easy at first to start identifying acids and bases in terms of the electron movement or how the electrons are going to behave, but there are a couple of rules of thumb that I want to give you for starting to think about acids and bases in this way. And so typically a base has either a full negative charge, or a partial negative charge, or a lone pair, so lone pair or lone pairs, or pi electrons. It can have any or all of these, honestly. What you're really looking for here is electron density. Okay, you want your bases to be electron rich. Acids, on the other hand, typically have either a full positive charge a partial positive charge, or, I should put or there, an incomplete octet. And overall, what we're looking for is electron deficiency. You want your acid to be electron deficient so that it can accept electrons from the base. So let's take a look at how pi electrons can act as a base in a reaction. We have in this reaction an acid that you should be familiar with from general chemistry, sulfuric acid, H2SO4. We know that H2SO4 has a very acidic proton on it, and so it wants to lose its proton. But let's think about this in terms of electron transfer. Since we're saying that this is going to be the acid in the reaction, that means it's going to accept the electron pair in the reaction. Therefore, the pi system is going to be the base in the reaction, and it's going to need to donate an electron pair. That electron pair is going to be the pi electrons that are shared between these carbons here. So we're going to start our arrow here, and we're going to end it at the proton that the acid is trying to give up. In order to give up that proton, the bond between H and O has to be broken. So let's take a look at what the products of this reaction would look like on the next slide. So we've established this much, and I think the easier part of this for you to see right now is going to be that one product of this reaction is going to look like this. It's going to be the deprotonated sulfuric acid, the conjugate base of sulfuric acid, which is HSO4-. So I'm going to finish filling in my lone pairs here. But what probably isn't as intuitive is what the organic product looks like. So all of this, the carbon-carbon structure, none of these sigma bonds were disturbed. But now you have a new bond between something and this proton over here that was lost. And since the pi electrons were shared between the two carbons, it turns out that the proton in orange came from the acid, also is going to be connected to one of those carbons. So the electrons came from the carbon, so they have to stay with the carbon. On the other side, you now have a carbon with a positive charge because it lost its electrons that it was sharing there. So this is another example of an acid-base reaction. Again, as a side note, always go back and check the formal charge. We have a charge, net zero charge up here. So that means that we need to have a net zero charge down here. We know that HSO4 minus, of course, has a -1 charge, but then it's canceled out by this +1 charge here. So always go back and check your charges. Let's take a look at another acid-base reaction. So right now, you may not be able to tell exactly which one is the acid and which one is the base. Let's think about our rules of thumb that we learned before. We're looking for, when we're looking for a base, we're trying to find something that has electron density to donate, so something with pi electrons, lone pairs, and or a negative charge or a partial negative charge. Chlorine looks like it could potentially be, because it has all these lone pairs, it could potentially be a base. But then you have this oxygen over here that could also be a base. If you think about basicity, an oxygen with a negative charge is going to be more reactive, more basic than a neutral chlorine would be. And so this hydroxide ion, as you may not be surprised, because you've seen hydroxide used as a base in general chemistry, it's also going to be a base in this reaction. So then you're left with, well, what could be acidic over on this organic structure? And it turns out, if you recall, there was mention of a partial positive charge that could act as a site of acidity. And if you look at the bond between carbon and chlorine, there's a dipole there. And so we have a delta plus, delta minus type situation here. And so it's going to be this delta plus charge that actually acts as the acid here. So if we were to draw reaction arrows for this, you would have an oxygen coming over and attacking this carbon. Then the bond between the carbon and the chlorine would break. Now we're not going to get into all the details of this at this particular time. The reaction that we're looking at here is something that we will study extensively in Chapter 7. But I just want you to get familiar with trying to identify who's the acid and who's the base in a given reaction. Sometimes it's not straightforward, but the more you do, the easier this will become. So to recap, when we are looking for a base, we're looking for an electron donor. And these are typically species that are electron rich. So we went over, lone pairs, negative charges, pi electrons, etc. And acids are electron acceptors. These are going to be electron deficient. So we're talking about incomplete octets, positive charges, And I want to give you two new names now that we've covered these concepts. When we talk about a base in terms of something that's electron rich, we actually are talking about what's called a Lewis base, but the term that you'll hear most often used to describe this is a nucleophile. So the terms Lewis base and nucleophile are interchangeable, but all that means is it's an electron-rich species. The term nucleophile, the name nucleophile, comes from the fact that the nucleus is a positive center, and so a nucleophile is a species that is seeking a positive center. So that would be something that's negatively charged or electron-rich. On the other hand, the acid, when we talk about the acid this way in terms of accepting electrons, we're talking about a Lewis acid, but the term that you will hear used more often than that is an electrophile. That one's a little bit easier to think about. If it's an electrophile, it's seeking electrons, so it's seeking a negative charge. And that makes sense with something that's electron deficient. So those are two new terms for you to start playing around with. And as you're working through problems and try to incorporate this into your vocabulary, and you will see this come up for sure in your textbook reading.